Welcome, everyone. My name is Linda Okanachi, and I'm a graduate student researcher at the University of British Columbia under the Persuasive and Social Computing Lab under Dr. Ifoma Adaji. And today we'll be diving into advanced research computing and high performance computing resources that are offered by the Digital Research Alliance of Canada. This training is there to specifically guide you on how to efficiently use um, the resources provided by the DRA of Canada. And so, whether you're a researcher, whether you're a data scientist or a data engineer, understanding these tools and maybe some core concepts could help you accelerate your projects and make most of Canada's computing infrastructure. All right, let's dive in. So in this session, we'll be looking at advanced research computing. We'll be looking at some explanations, some concepts to help you simplify your understanding of what research computing is. We'll be looking at some ARC resources, accessing and operating these ARC resources, and I'll also be giving you some tips on how to better use these resources for your projects. So, what is advanced research computing? So, advanced research computing typically provides you with computational tools, software, and infrastructure to support modern research. And it typically involves big data, simulations, AI. So what it does is it enables researchers to process massive data sets, run simulations, and perform calculations at speeds, far beyond what your normal computer or desktop can handle. And there's certain key features of advanced research computing, and one key feature is the high performing computing. And so what does this really mean? So what HPC does is it allows researchers to run complex simulations and calculations at high speeds using clusters or of powerful computers. And where can you use this? You can use this in AI training. For example, if you're a researcher that deal with deep learning models that could take weeks or months to run on a laptop, you could easily make use of the high performance computing that is offered through the advanced research computing to run your deep learning models. Another example could be like physics simulations. Say you're modeling a black hole or weather pattern or DNA folding, you would need a supercomputer to be able to run this. And what's better than a high performance computing feature to allow you to be able to do this. Now, so imagine you're an astronomer trying to simulate the formation of galaxy. This is just an example, please. Um, the simulation could take months, right? And your computer might overheat. But on an HPC cluster, the same simulation could be finished in a few hours or days because there are thousands of processors working in parallel. So HPC is like having, I don't know, 1,000 interns work on your research overnight while you sleep instead of doing it all by yourself. So I think the other future that I'm also excited about that the Alliance has is cloud computing. What cloud computing does is remove the need for expensive hardware, allowing researchers to run computations remotely from anywhere in the world, which is a massive save. And then you're able to scale resources up or down depending on their needs. And you can collaborate globally, by sharing computing environments. So imagine you're working with a research team across Canada or even Germany or Japan, right? And without cloud computing, everyone would have to install complex software. They would have to deal with compatibility issues. They would have to deal with how to exchange huge data sets. And this might actually be a nightmare. So with cloud computing, you can all work on the same remote platform, and all this while using scalable computing resources without worrying about hardware limitations. So I think I would liken um, cloud computing to something like Netflix, but instead of watching movies, you're running scientific models on demand, and you're also able to collaborate with different researchers, across the world. So this is one thing the alliance also provides. Another thing the Alliance provides is data management solutions. Modern research, produces massive amounts of data. We're currently in that age where we are dealing with big data. So the advanced research computing tools provides you large or storage spaces or large terabytes or um, storage spaces, large spaces for you to be able to store large research data. Also, you can secure sensitive information like, say, patient's medical record, financial models, and the likes on the spaces that are provided for you. So you could be thinking of a scenario. So you could be a genomics researcher. You're working with 3 million human DNA sequences. Without proper data management, your files could be scattered and difficult to find. But if you have ARC solutions or storage solutions, your data is systematically, organized, backed up, and you can easily retrieve it. Now, for the purpose of this training, we'll be focusing mainly on maybe the high performance computing and how to, submit a job. There will also be another video, upcoming sessions that would focus on how to access this cloud computing and data management solutions. So stay tuned. So high performance computing is not just about faster computers. It's like a network of supercomputers, working together to solve problems that are far beyond the capabilities of your standard machines. And so just think of it like this: a personal laptop is like, one person digging a hole with a shovel, but having the access to HPC is like having like 10,000 workers with excavators, digging at the same time. So this allows for massive parallelization and allows for the HPC systems to process your data thousands of times faster than your traditional computers. Now, how does HPC work? So HPC is a combination of supercomputers plus parallel processing. Now, HPC does not rely on a single processor like your normal PC. Instead, it splits your task across thousands of processors, and then it runs the calculations in parallel. And this is called parallel computing. And what this means is breaking a big problem into small parts and then solving them at the same time rather than just one by one, right? Now, in the term or the concept of HPC, we also have CPUs versus GPU clusters. So, what's the difference? Now, CPU clusters, they're actually good for general purpose tasks like running simulations, maybe statistical analysis, and numerical computations, while GPU clusters are specifically designed for massively parallel tasks like your deep learning, AI training, and even graphics processing, right? And there's also the concept of distributed computing, where it's like HPC systems use distributed computing, and that's like spreading out computations across many different machines, allowing scientists to analyze huge data sets and also enabling breakthroughs in maybe finance and AI. So the concept of HPC ensures that you have access to parallel processing for your high speed computation. Now let's take a look at where researchers actually need it. I think I mentioned this earlier that you actually need it in big data analysis. You could also need it in genomics, in AI, in scientific simulation, health, and medicine. So you see that what the tools that the Alliance offers actually cross across different borders, and it doesn't really matter the field you're in as long as you're going to be dealing with data of some sorts. As a researcher, you can, even as an independent researcher or a data scientist or a data engineer, you're going to need access to some of the tools provided by the Digital Research Alliance of Canada. So we talked about where ARC can be used. Now let's see when ARC is actually needed. So advanced research computing is not just about speed, it's about solving problems that are too large or problems that are too complex or too data intensive for regular computers. And so when do researchers actually need ARC? Like when a problem takes too long or when your computation is too big, you actually need ARC. So I'm just going to give you a scenario. So currently, my thesis actually involves using large language models for misinformation detection. And what this means is that I have to fine tune models that are actually very big in size and require absolute memory. It requires like big memory. And this means that what would take me days or hours to run, days or months, I mean, to run, I could easily use Arc to run it. And this is exactly what I did, because I remember when I started working with language models, I had to fine tune on my personal computer, and it took me days. It was running for days non-stop. It was a really slow process. But once I was introduced to Arc by my supervisor, I had to learn how to send jobs through the scheduler to the ARC system. And after my job was scheduled, in a matter of hours, I was able to get my computations, which was actually a big save and a big relief for me, because then I was able to make corrections quickly and also resend. So you actually need ARC if you're working with a data that is too big and maybe the problem takes too long. Like for example, the large language model scenario that I just gave. Now, what does ARC involves? Like I've said, it involves hardware, algorithms, it involves software, and also data management. Now, you might actually think that because Arc um, has more cores, that then it's faster, right? The short answer to that is actually yes, but only if used correctly. Now, adding more CPU cores is like hiring more workers, this is the scenario I've actually given from the beginning. However, just throwing more people at the problem doesn't always mean it can be done faster. So one of the aims of this training is to actually see how we can better use these resources and how we can use it right. So the real question is, can the work be split efficiently, across multiple cores? And the answer to that is yes. We're going to actually demo how to send your files to some of the clusters, and we're going to demo that on this training session as well. So let's dive into the ARC resources. So Canada has advanced research computing clusters designed to support high performance computing needs across various research domains, and each cluster is actually optimized for specific tasks. So ensuring that the researchers have access to right resources. The first one is the Graham, which is the general purpose computing. This is launched at the University of Waterloo, and it's actually best for HPC workloads, and it's suitable for broad research fields, including data analysis, simulations, and computational modeling. It also offers balanced CPU, memory, and storage resources. Now, one thing I want to quickly say here is this: I believe that these resources are also available in different countries. So, this training is also applicable to what's obtainable probably in the US and other countries as well. I'm sure there are also clusters or supercomputers that are available for research. So this can be applied, to other countries as well. We also have the CEDA, which is launched at the Simon Fraser University, and it's best for data heavy applications. This particular cluster is optimized for AI, machine learning, deep learning, and large scale data processing. So I think ideally this is for bioinformatics, social sciences, and even complex statistical models. We also have the Niagara, which is at the University of Toronto. This is for large scale processing, and it's actually best for massively parallel computations. So it's designed for scientific simulations, physics modeling, and it also supports highly parallelized workloads. And another one is Beluga. This is the one I use like a lot more. This one is for GPU intensive tasks. Like um I gave the example about the usage of LLMs. So when you're fine tuning LLMs, it's actually a very GPU intensive task. And this is at the ETS Montreal. And it's optimized for deep learning, AI model trainings, and simulations that require GPU. It can also, I think, be used for computer vision, natural language processing, and high speed AI inference. So you depending on your case study, you can always choose the right cluster for your project need. So in the previous slide, I talked about cluster, but you might wonder what a cluster is. So a cluster is a group of interconnected computers, so nodes. So you see here node 4, node 3, there is node 1 and node 2, all interconnected, right? So they kind of work together to perform large scale computations. So it makes computations faster and more efficient than just a single computer. So one thing you need to understand is the structure of the HPC cluster. The nodes, they're like building blocks of the cluster. So an HPC cluster may consist of multiple nodes like this, which actually has 4 nodes, and these nodes are all standalone. They are powerful computers. Each node, so node 1 has its own CPU, it has its own RAM, it has its own storage. So it's making it independent, and but it's still connected to others. Likewise, node 2, node 3, and node 4. And because they're interconnected, they communicate via high-speed network and allows them to share data. Node 1 can share data with node 2, and this means they can also synchronize tasks and work together efficiently. And each node has its own dedicated RAM, and it's not shared across all nodes. So this has its own RAM, which is not shared with node 2. And this system is what we call a distributed system, meaning the nodes exchange data by sending messages over the networks, and all the processes they access, they have their own dedicated RAM, as opposed to where you have shared memory, right? So they can communicate. They have their own RAM, their own CPU, and their own storage, but they are still interconnected. So in the previous slide, we saw what clusters are, and we visually looked at the nodes that make up a cluster. So a shared, let's look at what multi-core computers are. They're they essentially just have multiple processor cores within a single machine, and we have that's known as a shared memory system. So a shared memory system in a multi-core computer refers to that architecture where multiple processor cores are like within a single machine, and they have access to the same memory space. Now, it's advantageous in that it allows them to actually read and write data efficiently, right? Without needing explicit, maybe message passing like the way distributed systems are. But multiple cores on a single node, then you have like one large, maybe RAM shared by all the cores, and then communication happens, communication happens between all these cores, right? Through memory access. But I think one of the very advantages of this is that you have like lower communication overhead, faster memory access. But one limitation is memory contention. When you have so many cores trying to access memory simultaneously, it can actually create bottlenecks and scalability issues. But if you have you know yeah, so they can also be expensive for large systems. So as more cores are added, the complexity and cost also increases, and that's what's available on your desktop. I think laptop, I think it's the same kind of architecture that's also available. So one thing to note is that HPC systems are not they're not just powered by the CPU. They have specialized accelerators like your GPU. So you must have heard me mention GPU. The GPU stands for the graphic processing units, and this are actually used to speed up computations. So why do you use GPUs? Now GPUs are actually optimized for massively parallel tasks, and you can perform thousands of computations simultaneously. So it makes them really ideal for machine learning. However, using GPU requires effective specialized programming techniques. Now, so what are accelerators in HPC? So systems with accelerators, the GPU and TPUs, some of HPC nodes contain specialized hardware like GPUs to handle these heavy computations, like I mentioned before. And GPUs can run thousands of smaller tasks simultaneously, and it's more complex to program. And you have implicit versus explicit approaches, right? So now let's look at the implicit. So implicit programming has easier uses like frameworks, TensorFlow or PyTorch. For example, for my project, I make use of the PyTorch framework, and it automatically optimizes workloads for GPU. And researchers, you don't need to worry about manual parallelization, as there are libraries in PyTorch that can handle this. Then when we're talking about explicit programming, we are talking about more control, and in that you'll be using something called CUDA. So directly writing CUDA is for the NVIDIA GPU. If anybody knows the NVIDIA GPU, I can add like a link to the description of this video, so that you can read up about the NVIDIA GPUs, or maybe the OpenCL code, to give you more fine-grained control over how the GPU processes data. But for this, you require deep knowledge of GPU memory management and maybe thread synchronization. But for us to keep it simple, maybe after working on your data, maybe using your Python, or having your Python script, and you're ready to run it, and you know it's going to take large computations, you can easily just make use of a framework or that has libraries that you can easily use to manipulate these GPUs. If this part is actually unclear, you can always ask questions in the comment section. And if you like this knowledge we've given so far, you can hit that like button and also give us like a thumbs up. So far, we've seen some definitions, some terms like clusters. We've talked about nodes, accelerators, and we've also talked about what the Digital Research Alliance of Canada offers. Now, let's actually see how we can access and operate these ARC resources. For you to be able to access these resources, you have to be an eligible user. So, an eligible user could be a university researcher, a student, a government or industry partner. You also need to set up an account. I'm not going to go in depth on this particular slide, because we actually have a detailed video. I'll put the link to the in the description of this particular video. So that first video, it details how you can set up an ARC account, and how you can get your username and set your password. And it also talks about those who are actually eligible, and what you can access, and if you need specific resources for your project, how you can also apply for certain resources. So you can just check the link for that video at the description of this particular video. So when you set up your account and you are all set up and you've actually logged in, there's something you need to understand, which is the importance or the difference between a login node and a compute node. So you can avoid performance issues and you can efficiently use your resources. So what's a login node? Now, when you log into an HPC cluster for the first time, the login node is what you encounter. And in the login node, you can write and edit code, you can manage files, you can submit your job scripts. In fact, you can actually, from the login node, create the .sh file. We'll come there much later in this video. And from there, you can also submit your job script to the cluster scheduler. Now, what you should not do on your login node is run large computation or CPU intensive tasks. You should also not train deep learning models directly on your login node, or do any simulation of your large data sets. I think maybe an illustration for this would be to think of the login node as like a receptionist desk in an office. You go there to check in, organize your work, and submit task, right? The way you'd go to the receptionist or maybe a particular office, but you don't actually do the heavy work there. That's for the compute nodes. The compute nodes are the ones that have dedicated machines for running large computations. And to access the compute nodes, you must submit a job script to the scheduler. And the scheduler used here is called SLURM, SLURM. And you must submit a job script to SLURM, then requesting resources. Now, this might all sound abstract, but we are going to give a demo to that, um, for you to access both the login and the compute node. Now, when using HPC resources, researchers need to, efficiently manage their storage and their compute time, so they can ensure like smooth research workflow. And their HPC clusters actually provide different types of storage. Remember, we talked about storage, and each storage is actually optimized for different specific research needs. One of the storage available is the home directory. This one is persistent, but it's small. It's about 50 gigabytes, and it's used for storing scripts. We're gonna show that when we actually do the demo of logging into an actual cluster, because I do have an account, and then I can show you what I mean. Then the scratch space as well, and the scratch space is used for to hold high speed temporary storage optimized for running your jobs. Then we have the project storage. In the project storage, you can store long-term projects, or long-term. It provides long-term storage for specific research projects, and you can share with other team members. Also, you can also manage the compute resources in sorry, the compute allocations in HPC, and request for more compute time. You can also track what you submitted through the SLURM to the compute node using certain key commands, and in due time would also show this. We've actually talked about the resources offered by the Digital Research Alliance of Canada, and what makes you an eligible user, and what you can find in terms of storage, clusters, and other available resources. Now, ARC systems are actually remote, so how do researchers access ARC systems? So whether you're working on a laptop at home or a workstation in a lab, your machine is actually a gateway to these HPC systems. So because the Arc system is a powerful supercomputer, it's housed in a secure data center. You connect to it remotely over the internet using SSH. Now, SSH is a secure shell. It's a secure command line interface that allows users to log in into remote HPC systems. And in so doing, it also encrypts communication, ensuring secure data transfer and remote access. So if you're using a Linux or a Mac OS, you can use the built-in terminal. You just need to run your bash and then type in SSH, your username, because you'd have to have a user account by now. Then at the cluster name.computecanada.ca, we're actually going to do this so you see what it looks like. Then on Windows, you can use a software like PuTTY or just a command line interface to establish an SSH session. And just in a few minutes, we'll see what that actually looks like. Different types of clusters, but for demonstration purposes, we're actually going to log into the Beluga cluster. I'm going to do that now. So let's attempt to log into the Beluga cluster. For that, we would have SSH, then your username. If you don't have an account with Alliance, you would get your username. So then Beluga, which is the name of the cluster we are trying to access, then .computecanada.ca. Mind you, you can actually use .alliancecan.ca. So this was the first one I actually encountered, the Compute Canada. That's the reason why I'm using it. Then you click on enter. It would ask you for your password. If you have an account, you would also have a password. Then now so it uses a multi-factor authentication, and for that reason you'd need to have the Duo Mobile or the Duo Push app on your Android phone, so that you can get a passcode given to you. You enter that passcode without any need for spaces between the numbers. Then you click enter. As you can see, we are logged into the Beluga cluster, and if you'd notice something, we are in the login node. So this is actually very different from the compute node. So please take note that this is different from the compute node. Now that you've seen what the login node looks like, and we've been able to access Beluga, I think another thing we can do is also to transfer files. Now, usually when you're working with Python scripts, or you're working with anything data, you typically, have a data set, and then you have like your Python script, and you want to be able to transfer this to the either the home directory or the project directory, or wherever you want to store it, so that it's easier for you to run your jobs. So I'm going to show you how to transfer such files. You can actually transfer the files on a different command line interface, different from the command line interface you use to log into the Beluga cluster, or you can just use the same one, but you have to do this even before you log into the cluster. So let me show you. So in my case here, I opened a new command prompt to be able to transfer files. Like I said, you can open a new command prompt to transfer the files and then verify that the files were actually there. So I mentioned that we have certain directories where you can transfer your files to, and you can use the home directory if you want. And one of the key features of the home directory is that it has persistent storage. So the files are not automatically deleted, but you have limited space, I think around 50 gig max. And you can actually use them for storing code files, SLURM scripts, VMs, but you can't use them for running jobs. But we can actually transfer to the home directory. I can show you how to do that. Then we can move it to scratch if you want to, run actual jobs. So let's transfer. I have, the first thing I'm supposed to do is to navigate to the directory where my data set is and my Python script. So ideally I have them on my desktop. So if we navigate to that directory, we are currently on the desktop. Then we have SCP, the name of the file you are sending. In this case, it's diabetes_cleaned.csv, your username, then at the name of the cluster, which is beluga.compute Canada. Remember, you can use alliancecan.ca, compute canada.ca. Then now you need to specify where you want that file to, to go. And then you put a semicolon, and this stands for, this is showing you that it's going to go to the home directory. Then you click enter. Now it's going to ask for your password. You can just enter, your password and click enter. Like I said, we are going to be making use of multi-factor authentication. I think you saw that when we were trying to access the Beluga cluster. So you have dual file or dual push app on your phone. You can then enter the numbers or the passcode without any space and click enter. So you can see that this is loading, right? This is loading to be sent to the home directory on the cluster. Would verify that. Now, the second file I want to transfer is actually the content filtering.py file, right? Content filtering dot the file extension name, your username at the name of your cluster, dot compute canada.ca. Right, and remember we are sending this to the home directory. This is just like a an example. You do the same thing. You enter your passcode, your password. Then you enter your push mobile passcode. Okay, so you can see this is also sent already. Now we need to go to the cluster to actually see if what we sent is actually there. So I think I have that already opened somewhere here. So I think you can see everything on the directory. You can see something like this. You can enter this to view everything in the home directory, but it also shows you everything on other projects or Scratch directory. So if you see here, you have your content filtering.py file. It's right here. You also have the diabetes_cleaned.csv. It's right here. But the thing is, we can't actually run them, in the home directory. We can run them if you'd want. I think it's just recommended to actually run them on Scratch. So for that reason, we can actually move the files from this place from the content filtering.py, this content filtering.py under the home directory, we can move them to Scratch so that we can submit our jobs. So what I'm going to do is right here, I'm going to move this to Scratch. And to do that, you can have something like this. So we're going to move. That's the name of the file. Now this indicates that it's currently in the home directory. Right. I think there should be like a space here. Then I think we should take it to the Scratch directory. Okay, another thing we can do is to also move this one, to move the content filtering. Right, I think .py, then we're taking that to the Scratch directory as well. So let's actually verify that what we have moved or what we have done is in the Scratch directory. Just the same way we verified that the other one was in the home directory. So you can see we have content because I had transferred an IPYNB file before now. So you can see that we have all this in the Scratch directory. So this is how you actually transfer files on your command prompt on Windows. I'm actually using a Windows system. Now the commands are a little bit different for a Mac system, but this is how you actually transfer files or commands for your to your cluster or to any directory. You can actually transfer first to the home cluster, to the home directory, I mean, and then move around depending on which directory you want to run your project from. But ideally, you want to run from Scratch. Yeah, so that's how it's done. All right, after submitting your after transferring your files to the necessary directory, the next thing you want to do is to create a job script, and you can have the .sh or .slum extension, and then you specify batch parameters. When you open the text editor, you have to specify the batch parameters, the S batch parameters, and I would explain to you what each parameters actually mean. Then you can use the S batch to submit your job to the compute node on the cluster and also monitor that job. All right, let's demonstrate that. So now that we've transferred the data set, we've transferred our files, we transferred them to the home directory and then we moved them to Scratch. Okay, so we're going to run the computation or submit the job on Scratch. But before I actually create the text editor for that, I want us to take a look at the content.filtering py file. The reason why I want us to do this is to just take a look at what dependencies we might actually need. So I see that I need touch, I need transformers, and I also need pandas. Now this is a very simple script. It's just for inference and for it's just for inference purposes, and it's just going to do infer maybe true or false from the first 10 samples. So I'm just going to show you how to submit. We'll not really go in depth in this particular video. I'm just going to show you how to submit and how to specify your resources. So now that we know the dependencies, there are two ways to specify your dependencies. You can actually specify like by creating like a VM, like a virtual environment, not VM, I mean like a virtual environment, and then using pip install to install those dependencies. That's actually the recommended method. But just for showcasing how to submit, I'm going to do that in the slum or .sh file. Remember that I said you can use .slum or .sh to submit to a compute node on the cluster. So the first thing we'll do, remember that we have this on Scratch, right? So nano would actually would navigate to the Scratch place and then the Scratch directory, and then maybe create like a text editor where you can then
Nano opens like a text editor where you can then specify your S batch parameters. In this case, maybe we could call it computing. Let's just call it computing.slum. Okay, so computing.slum. So you see, it opens like a text editor, and we'll add the slum directives to allocate resources and install dependencies before running our script. So, like I said, in a real setup, we'd want to use a virtual environment, but for this video, we just install directly inside the slum script. So let's do so. So we would have this. So now let's start specifying. So let's first specify the job name. In this case, the job name, I want maybe the job name to be, these are S batch parameters, just in case. So I want the job name to be, let's say, let's call it bet underscore classification. That's my job name. That's the job name I chose. You can specify another parameter. Let's say we're specifying time. The script is actually very simple. So I'm just going to say, maybe maximum of just an hour. Just an hour. Let's specify another, parameter. Now, in the next slide, I'm going to explain what, Slum is and, all these parameters as well. So this is a single task job. Let's specify another parameter. I'm just going to give, I thought of actually putting, giving CPUs and maybe just one GPU because what I'm running isn't much, but I also gauge that breadth, it's kind of computationally heavy. So I'm just going to give the CPUs 4. So memory, we can have like 16 gig, like 16 gig RAM. Okay, so I'm just gonna specify, just one GPU. Okay, so I want to save the logs in Scratch as well. Okay, so we're gonna have, let's just call this maybe birth, or let's say output. Oh, there's supposed to be like a stroke. So let's say output underscore birth.log. I think one final parameter for error logs, and I still want to store it in Scratch, right? So error logs, in this case, would have, so maybe we can call this maybe birth underscore error. Any name you decide is fine. Okay. Okay, so this is a Python script, so I'm going to load the Python module. Ordinarily, I should have shown you guys how to see what software is available on the cluster. You can use module avail, but you actually use that on the login node. But there'll be a detailed video on dedicated to submitting jobs. Then we're going to actually fine tune a model and then submit, see how it's done, look at several things on the queue, what they mean. But this is just, just to show you how it's done for just submitting only. We're not going to go into detail. Now remember that we saw 3 dependencies, right? Yeah. So we saw 3 dependencies. So we want to install them at this point. So I think dependencies we saw were touch, transformers, and pandas. I think we also saw pandas. Um, so remember that we stored in the scratch directory, so we can navigate to that directory so that it easily accesses the files, and we can then run the script. The script we're running is the content filtering script .py. Okay, so this is what we're running. So I'm just gonna go through. Okay, so the script tells Slum, in essence, so this is just like an interpretation. The script tells Slum to allocate 4 CPU cores, 16 gig RAM, and 1 GPU. Then he installs Touch, Transformers, and Pandas before running the content filtering.py script. So I'm just gonna go through the SBatch parameters just to be sure that there's no mistake. So this is time, this is end task, CPUs per task. We specify that as 4, 16 gig GPUs output. Okay, yeah. So this is basically this is just what a simple Slurm script looks like. When you're done, you click on Control X, I believe. Then you see these two here, yes or no. So you're saving it, right? So you click yes, right? Then you click Enter. So we've done that, right? So just to be sure that it was properly saved and the content is not actually empty, you can use this command cat. Then we have everything in scratch. So scratch, I think we named it computing.slum, right? So let's see if everything is fine. So computing.slum. So we see our content, right? So it's all saved there. Now that we've confirmed that our script is ready, we can then submit. And how do you submit? You make use of SBatch. This is in our directories, in the scratch directory. So scratch, um, I believe this is um computing. Let me confirm the name. Yeah, so computing. So computing dot slum. Now, if it's successful, it shows us the batch job number. So we can see that we have submitted batch job 53862741. So this is submitted already. And then we can also see this in queue as well. For that, you enter SQ, enter this command, I think user. So you can see this, it specifies also this job, which is 53862. So I submitted the job previously, 5386271. You can see it's running. It shows that it's running. So this is essentially how you submit. Now we're going to, in like a different or separate video, would actually try to see other things like monitoring the job output in real time, and also getting our outputs, looking at what it actually gives us. So this is it for submitting a job.
So in the last slide, you must have heard me mention something called SLURM. Now, what is SLURM? SLURM is actually a scheduler in HPC. It's responsible for managing multiple job requests because as a user, you're not probably the only one accessing the Beluga cluster, like I showed you how to. Other students from different schools, other researchers, other labs, other teams are also accessing the cluster probably at the same time as you are. So it's a scheduler. It helps in managing multiple job requests from different users. It also helps in allocating compute resources. So like you saw under the when I was preparing the job script to be submitted, I specified certain resources like GPU, size. I specified so many things that I wanted, right? So it's Slum actually helps in allocating these compute resources based on availability and priority. So if your job is going to require more resources, you kind of are in a queue.
and it's able to then schedule them to you when it's available. It also prevents like system overload and ensures that there's a fair use of the CPU, memory, and GPU. So why is scheduler actually needed in HPC? So without a scheduler, the cluster would be chaotic because you'd have a lot of users competing for the same resources and there'll be inefficiency. So with a scheduler like SLURM, you get optimized resource allocations, fair sharing of your compute power. So if a lot of users are trying to access at the same time, that would be chaotic. And the SLURM is actually scheduler used in the Canadian HPC systems. Now, I'm actually sure that there are other, I'm not really specific, but there should be names of other schedulers that are used by other similar systems, maybe in the US, maybe in other countries, as well. So SLURM allows researchers to submit job, and we're going to talk about the commands that you can use to submit job, that you can use to check your job status, and you can use to cancel jobs, and also run interactive sessions. Now, one thing I should point out at this slide is that we actually ran through the session for submitting jobs. We didn't really go into details to actually see some of the commands and how it can be used, right? But in another video, we would have a video dedicated to submitting jobs on the compute node, and commands that you can typically use, maybe to remove files, maybe to check the your process that's running, to check the outcome, and also see the like real life outputs. We're going to have that as well. I don't want to make this video unnecessarily long, so there's going to be a dedicated video for that. So when submitting jobs to an HPC cluster using SLURM, researchers must specify resource requirements using SBatch parameters. So I don't know if you noticed when we were submitting that job on the compute node, we specified some parameters using SBatch. So I just want to break down some of the most commonly used SBatch parameters and how to use them effectively. So what is SBatch? So the SBatch command is used to submit batch jobs to Slurm scheduler. It tells the Slurm how many CPUs, GPUs, memories, and nodes that particular job you're submitting requires. So if you don't specify parameters, Slurm assigns default values, and that's the problem. So if you don't specify, let's say you're specifying how long your work should run, you can just gauge it, especially if you've tried to run the job before and maybe for 2 hours on your CPU it was taking so long. You need to specify a longer period of time. If you specify a short period of time, your job can be cut short. And if you don't specify parameters, right, Slurm assigns like a default value and it may be insufficient for your task. So there are certain SBatch parameters, like for example the amount of time. Now if you request 2 hours of compute time, your SBatch time will be cut to 2 hours. Like I said in another video, we're going to specify some of these parameters and then send it to the compute node for running. Now if your job exceeds the time limit, Slurm will cancel it automatically. Now, so always estimate runtime carefully to avoid any form of interruptions. Another thing is the number of nodes. You need to define how many physical nodes your job requires. So you can request 2 nodes. In that situation, you'd have SBatch node equals 2, right? Why does this matter? Because large parallel jobs may need multiple nodes to distribute computation. So if your job fits on one node, requesting multiple nodes, would actually waste resources. Another thing is number of tasks, which is the end task. You need to specify the total number of processes your job will run, like requesting maybe 16 tasks or 16 processes. Now, what this does is, or why this matters, is that it's actually used for specifying the message passing. It's actually used for MPI jobs, yeah. So MPI jobs are jobs that actually require or run on multiple processes. So message passing interface, that's meaning of MPI. So more task means high parallelism, but don't request more than you need. Another is the number of tasks per node. Now this actually controls how many tasks run on each node. If requesting 2 nodes with 4 tasks per node,
then you'd have to have something like S batch node equals 2 and S batch n tax per node equals 4. I know this is somewhat abstract and would only be very clear if you're actually seeing it being specified, and then maybe we take a look at a simple Python script and then we can guess or gauge how many nodes, how many n tax would need, the time and things like that. And this is what we're going to do in the video I keep talking about. Now, another is the number of GPU, right? You need to know the number of GPUs per node. GPU can be used when you are running GPU accelerated jobs. For example, when I was running BERT on Google Colab, now usually I was just using CPU first, and I noticed after some time it was like it glitched and it crashed. It was like saying, oh, not enough memory, not enough power to be able to run this. So I had to use the T4 um GPU on Google Colab for, I think it's given for a specified period of time. Then I was able to run the job. But you have just a limited time to use that on Google Colab. Subsequently, it's actually paid for. There's also the NVIDIA A800, and there are different types of GPUs. We'll also cover that in that video. Then you can also use reserved nodes. Now, if you have reserved nodes for special projects, you have to specify the reservation. Now, if you're using a reservation, jobs outside of this reservation won't actually run on this particular node. Now, so these are some of the SBatch parameters that we have, and it also specifies, exactly what you can do with them when you're trying to run a job on any of these HPC systems or access the cluster. So what you just saw are SBatch parameters to specify the compute resources that you use to submit or schedule your job, right? Now, there are also commands to interact with the scheduler, like the SBatch. So what we just saw was the SBatch parameters. Now, if you want to see queued jobs, I'm going to also show this because it can show you if your job is in queue, if it's running, you can use the SQ. If you're canceling a job, you use the cancel command. And if you are seeing the job starts after completion, you can use the SEFF. And then to get like short interactive job on a compute node, you can use salloc. We're going to use all these commands so that it's more clear. Now, this is just like a brief overview. So I think in summary, what we've seen is this diagram outlines what it is from user to submitting a job. Now, the user starts any process, and the user could be any researcher, any scientist, any developer who is running computational task on the HPC, system. And then remember we logged into Beluga, right? So then you log in, and at that point where we logged in, I showed you the login node. From there, you prepare your job script and specify your S batch parameters. And from there, you submit your jobs. And with the SQ, you can actually see your job in the queue, how long it will take. It's specified there. If your job is currently running, the scheduler then, you get it. Scheduler then sends this to the compute node, right? It sends to the compute node, and once the scheduler finds the best available compute node, it assigns the job to them, and the job then runs on that allocated compute node until completion. So this is typically what happens once it finds a particular space for it. This is typically what happens on an HPC system. Now, when the job finishes, the outputs are actually saved to an output file that you will specify, and you can also check the logs to see if there were any issues whatsoever whilst the job was running. So the user can then download the results using SCP. Same SCP we use to transfer the files can also be used to download the results, or you can actually analyze them directly on the cluster. Now I'll leave you with some final tips and conclusion. Okay, the first step is to not, run your job on the login node. Remember when we first logged into Beluga, that passion that I showed you was the login node. So you do not run your job, there. You're on the login node, and there's no need to run heavy computations there. It slows down the system for other people as well. So you use the login node to write and edit your job script like we did, and then you transfer files to cluster, and then you submit using SBatch, and then you specify your SBatch parameters. You do not run
right there on the login node. The second tip would be to optimize your job request to avoid wasting resources. So ideally, after running NLP models for a while, I've discovered that a lot of them take around 3 to 4 hours to be completed. So it would be wasteful of me to request for 8 hours when the job can actually run for just 4. And I've discovered that if I have an NVIDIA A100 GPU, it runs even faster. So I can request for that and just maybe one core. So I think we should have like maybe a session where we can look at a job and then determine how long this will take and what we typically need and how you can calculate that. So if your program would run with 8 gig just fine in terms of memory, don't request for 128 gig. This would waste, resources, and HPC systems actually have limited compute power, so only request what you need. So the more compute resources that you request for, the longer your jobs, and your jobs might wait in the queue for a really long time. So only request what you need. So the third tip is to actually plan ahead for compute time resources. Now, there's some jobs, especially if you're working in a team and it's a very large job. For example, so for NLP models, there's something called pre-training where you have to train a model with large files or with large amounts of data, usually in millions, right? And that is going to require special allocations or grant applications for how to apply, and the tips and tricks you need to apply for such allocations. You can check our video. The link of that video will be in the description below. And for that, you need to see if your project requires that. If it's going to require long run times or GPUs, such projects actually run for a long period of time, say 1, 2, 3 weeks, and that's a long period of time. You're going to actually need to apply for the resource allocation competition so that you can be in priority queue for compute resources for that kind of projects. So you need to apply early. And the Digital Research Alliance of Canada has deadlines. Usually they announce it, and I can also put a link to the Digital Research Alliance of Canada's website, so you can see the call for, I think last year, what the application looks like, and tips to ensure that you're able to apply early in the research cycle for your project. So if you want to learn more about Linux, scheduling, programming, research data management, you can actually check these links. They're actually important, and it also outlines the training calendar for DRA for several projects, and also regional and regional LMs and trainings as well, because the Alliance offers several courses that you can use to get started, especially if you're going to be working with a lot of data and you need computational resources for different types of projects, even as a developer. So in conclusion, ARC and HPC are actually essential for research. It makes your life easier, and just look at it that you can actually request for these resources and have them for free. Because if you'd be using collab for some of these resources, you might need to pay, but for this you kind of get these resources for free, and you can submit jobs at any time without wasting time. And you can optimize your resources. You can avoid long queue times. And what will be the next step for you as a researcher? You need to practice submitting jobs and testing some of the commands to see what they can do and how they can help you. And you need to learn advanced job scheduling techniques to improve efficiency. Like I said, the links I showed in the previous slide provide you with available training and support resources. Now, if you have specific questions and you try one of the links, maybe technical support at DRI, you should be able to reach someone who could provide insights. Meanwhile, you can also join our DRI Axe space, which I'll place the link to that on Slack in the video description, where you can ask certain questions, and you can also get help at any time with your projects or submitting jobs, or even if it's just accessing and seeing what the login node, the computer node looks like, or just taking a look at your script to see how we can better optimize it.
for a better workflow. I feel like mastering some of these things are actually essential for your research, and it can help you optimize your workflow, make you better, and also, prevent you from wasting time. Thank you for your attention. That will be all from Pascal Lab. Thank you very much.